1 on the sheet asks you, how can you determine if an object is in motion? Now, there are a lot of ways to say this, but the key thing I would be looking for in an answer for number 1 is that its position compared to a reference point has changed. So if you said anything about a starting point, an original point, something where you're comparing where the object is before and after, any of those things are telling me that you would compare the object to a reference point and see if its position has changed. This question will just be out of 1 mark, so as long as you have mentioned comparing it to a reference point, you have the correct answer. Does anyone want to ask questions about number 1? So then in number 2, there are actually 2 things that I'm looking for, so it will be out of 2 points. Number 2 asks you, when is an object traveling in uniform motion? So there are 2 conditions. There has to be a constant rate, or if you said the same speed or the same rate or a constant speed, any of those descriptions mean a constant rate. And it has to be traveling in a straight line. Does anyone have any questions they'd like to ask about number 2? So then number 7 asks you, of the 3 scenarios that are there, which one of them best represents uniform motion? Now, I think that you could make a case for any of them, as long as you described one of these 2 points. So in your answer to number 7, no matter which one you chose, if you said it's because the thing is going in a straight line, or it's because the object or the person is traveling at a constant rate, that would be good support for your answer. I will tell you that I think C is the best answer, and I'll tell you why. I think C is the closest to going at a constant rate in a straight line. And the reason I think this, and you don't have to have said all of this in your explanation, but the reason I think this is because there is the least effect of gravity and the least effect of friction, in my opinion. In both A and B, an object is falling from a height higher to a lower height, whether you're sliding down a slide and there's friction, or it's water falling off of a waterfall. In both of them, gravity is affecting the speed of the object. And we'll see in our next section that gravity makes things accelerate. So it makes them change their speed, so the rate is not constant. On the water slide, very obviously there would be friction because the person is touching the water and touching the slide. Even with the waterfall falling, the water is still entering in contact with air, and there would be friction there. In the electrical current moving through a wire, I'm aware that not all wires are perfectly straight, but a lot of the time a wire goes in a nice straight line. Since electrical current is made up of small, tiny particles called electrons, the effect of gravity would be really minimal on something that has a really small mass. And generally, there is not a lot of friction. There's not zero. I'm not saying that there's none. I'm just saying that I think this one has the least effect. So we're just going to make number 7 out of 1. As long as you gave one of the points about uniform motion as support for your answer, I'll accept any of A, B, or C. Would anybody like to ask any questions about that one? So then 8, 9, 10, and 11 are all calculation questions. So I'll put down the answers first, and then if you'd like for me to go over them, I will. The answer to number 8 is 4.17 meters per second. The answer to number 9 is 1.50 seconds. The answer to number 10 is 4.06 times 10 to the power of 3 kilometers. And I'll talk about number 10 because usually that's one that people have a question about. The answer to number 11 is 5.00 hours. Now for each of 8, 9, 10, and 11, I would make a calculation question out of 3 marks. One of the marks would be showing the calculation that you did, showing your work. Another mark would be, do you have the actual right answer? And the third mark would be 0.5 for the unit, 0.5 for significant digits. So if all you did was round your answer incorrectly, you would get 2.5 out of 3. If all you forgot was to put a unit, you would get 2.5 out of 3. Now for number 10 specifically, I just wanted to show you that the actual answer is 4,059 kilometers. And I changed that to scientific notation so that I only had 3 significant digits. The way I did that was by taking the decimal, which would be after the 9, moving it 1, 2, 3 spots so that there was only one number in front of the decimal. Since I moved it 3 spots, I used 10 to the power of 3 because that's how many places I moved the decimal. Now, would anybody like for me to demonstrate the calculation that you need for any of those 4 questions? Yes, George. I sure could. In number 9, we are asking for the time. So for number 9, time, if I rearrange the formula, is the change in distance over speed. The change in distance was 45.0 meters, and the speed was 30.0 meters per second. So I ended up doing 45 divided by 30, and that's how I got 1.5. I added the extra zeros so that I had 3 significant digits. So on my calculator, it would have just said 1.5, and I added the 0 to have the correct number of significant digits. Would anyone else like to ask about any of the other calculation questions or this one? So then the last one was number 19. Number 19 asked you, why is it so difficult to find examples of objects that are traveling in uniform motion? And I'm going to highlight these 2 points and say that it's because of things like gravity and things like friction. I could use the word forces if I wanted to be more general, but there are forces acting on objects as they are moving, preventing them from going at a constant speed or preventing them from going in a straight line. So those would be 2 examples of a force that's preventing an object from going at a constant speed. If you were taking this straight line part of uniform motion, you might mention things like not all roads are perfectly straight, and if you're traveling on a road, sometimes you have to turn. And so you could be very general, or you could give a really specific example. As long as you tell me what it is that I'm not able to do, that would be a good answer for number 19. Number 19 will just make out of 1. So if you add this up, it should make 17 altogether. If you could please make a total out of 17, put your name on it, and I'll collect them, and that'll count as today's daily review. All right, so the other thing that we'll talk about today is what you can learn from a graph. Now, you will need to make some graphs as part of your lab and as part of other assignments as well. So I need to make sure that you know what a graph looks like, what goes where, and what you can learn from calculating things on a graph. So the first slide of notes that you have on the handout I gave you talks about distance-time graphs, so that you know when we're looking at graphs in this unit, the vertical or y-axis, which is this one, and the horizontal or x-axis have specific things that go on them. What you'll see is that time is always going to be on the x-axis. In all of the graphs that we're going to look at, time is going to be on the x-axis. So we're going to look at distance time and speed time graphs, and in both of them, time, if it's around, is on the x-axis. What goes on the vertical axis will change. In this particular example, it's distance. But as long as you know that time is always on the x-axis, you know that the other thing will be on the y-axis. Now, a distance-time graph helps us describe motion. So we don't have to just describe motion with words or with numbers. We could describe it with what a graph looks like. If you look at a graph and you see a straight line, that means uniform motion. And that's what we're talking about in this section right now. So your graphs should have straight lines in this section. Later on, we'll see that curved lines describe non-uniform motion. And so in the third section, we'll talk about acceleration when speed changes. And we'll see that the distance-time graph will look different. But for now, we're going to focus only on straight lines. So on a distance-time graph, what we're usually interested in is something called the slope of the graph. Now the word slope, if you think about it in terms of skiing, and you ski on the slopes, which are mountains, is usually talking about how steep something is. And that's realistically what we're trying to determine. This line is the line that interests us. And when we say the slope of the graph, we really mean the slope of that line. How steep is that line? The steeper the line, the faster we know the object was going. So that you know, if we make some generalizations, a steeper line means the object was moving faster. So if you'd like to think about what steep means, imagine that you're going to go skiing, and when does it get scarier? When it gets more and more and more vertical. The flatter the slope is, the easier the run is. And so steeper slope means that the object was moving faster. Now, how do we calculate the slope of a graph? The very general formula for slope is something called rise over run. The rise is always talking about the change on the y-axis. So the little triangle means the change. The run is talking about the change on the x-axis. So no matter what type of graph we're looking at, we're always going to assess how much did the values for the y-axis change, and how much did the values for the x-axis change. In this particular type of graph, since the y-axis was distance and the x-axis was time, that's what we're going to calculate. Now you'll notice on your formula sheet, when I write the formula for slope, I didn't write 4 different versions of the slope formula. I wrote one that says it's the change in y over the change in x. That way, you can determine what was on the x-axis and what was on the y-axis. Now, I want you to take a look at this formula and think about what formula that actually looks like. If you think about final minus initial distance and final minus initial time, isn't that exactly the way that we would calculate speed? That's the formula for speed. So we already know this formula. We did this yesterday. Now I'm telling you, you could read this off of a graph instead of me telling you with words what the values are for each of those things. So when you would like to figure out the slope of a graph, you need to pick 2 points that are on the line. So I'm going to pick these 2 points that are sort of highlighted by little arrows. You don't have to pick any particular points. As long as you're picking 2 points that are on the line, you can calculate the slope of the graph. Now the idea is that you'll always read your graph from left to right. So the point that you pick that's the closest to the left will be point number 1, or the initial point. The point you pick that's the furthest to the right will be point number 2, or the final point. And it's important that you number them this way, because we're always going to tell you, take the final minus the initial point. And you might say to yourself, well, that's easy. I'll just take the big one minus the small one. But we'll see in the next section that lines don't always go up on graphs. Sometimes they go down. And so it's really important that the one that's on the left is the first one, The one that's on the right is the final or second one. So if I'd like to calculate the slope of this graph, I know that slope is rise over run. In other words, the change in y over the change in x. And in this particular graph, that means the change in distance over the change in time. Now, when you're writing out a slope calculation on a quiz or on a test, you don't necessarily need to show me this entire process that we're going through here. I just like to make sure you know why I'm taking distance and time as the values in this graph. So I'm going to take final distance minus initial distance over final time minus initial time. This is a spot where initial time and initial distance aren't necessarily going to be zero like they were for a lot of the calculations we did yesterday. According to my graph, for point number 2, the distance is a little bit less than 40. Now, here's an example of why you need to use graph paper. If I had graph paper, I would be able to be more accurate about what value that actually is. I'm just going to say, for saying's sake, that that represents 39 meters. The distance for point 1, or the initial point, is something just underneath 10. So I'm going to say, just for fun, that that is 9 meters. And so the way I knew the final distance and the initial distance was by picking a point on the graph and then going across to the y-axis and seeing what value that matched up with. When you're doing this, I recommend that you use a ruler or a piece of paper or something that is flat so that you are sure you're reading the correct number off of the graph. On the bottom, I'm going to do final minus initial time. So if I follow this point down here, for point number 2, the final point, it looks like my time is just under 4 seconds. So we'll say 3.9 seconds. And for point number 1, or the initial point, it's just under 1 second. So we'll say it's 0.9 seconds. Now here is a point where knowing how the order of operations works is important. You need to remember that when you have a fraction, it's like you have brackets. You have to do the subtraction on top and on the bottom before you do the division. So before I start dividing anything, I'm going to subtract these numbers. That means that I'm going to have 30 meters divided by 3 seconds. So I have to do those subtractions first, and anytime you're calculating slope, that will be true. You've always got to subtract the 2 before you do the dividing. Now my answer that I'll end up getting is 10 meters per second. Now I know it's meters per second because I was taking meters and dividing them by seconds. I also know it's meters per second because I remembered that the slope of a distance-time graph tells me the speed of the object, and speed is measured in meters per second. Now, if I'd like to be more precise, my answer should probably only have 1 significant digit. If I look at the values up here, these all have 2 sig digs, but these all only have 1 significant digit. So I'm going to put my answer with 1 significant digit. That means that instead of writing 10, I'm going to write 1 times 10 to the power of 1 meters per second. That way, only the 1 counts as a significant digit, and the whole times 10 to the power of does not. So this is an example of how you calculate slope and which values you would use off of a graph. So, if you have a question that you'd like to ask about anything that is on this slide, significant digits, calculations, order of operations, anything like that, Please go ahead. So this is one thing I would ask you to do. Actually calculate the slope. Question. So when I'm doing scientific notation, the plan is always that I take the decimal and move it so that there is one number in front of it. And I wanted to get rid of that 0. I didn't want two significant digits. So it's because my number was 10. Does anyone else have questions that they'd like to ask here? So like I was saying, actually calculating the slope is one thing that you'll have to do. But another thing that I would ask you to do is, without using actual numbers, just describe the motion of objects based on the way that a graph looks. So on the next slide, you will see a picture that doesn't have any numbers on it. Since this is a distance-time graph, time will be here and distance will be there. But there's no actual numbers. So if this was the graph that I gave you, I would not be asking you for an actual number. I would be asking you with words to describe how these objects were moving. So let's compare 1 and 2 and 3. If I compare number 1 and number 2, which one of them is going faster? Well, even without looking at numbers, you can look at the steepness of the line. So ask yourself which one of them would make a scarier ski hill, and I hope your answer would be number 1. Number 1 is moving the fastest. I can't say how fast it's moving, but I know it's moving the fastest, and that is because its slope is the steepest. Now, number 2 is moving, but it's not moving as fast as number 1. So I could simply say that this object is moving slower than number 1. I can't say by how much because there's no numbers on the graph, but the slope is not as steep, so I know that it's not moving as fast. Now, object number 3 is different. Can anyone tell me what object number 3 is doing? Sorry? You would think it's doing uniform motion, but I can't actually describe this as uniform motion. I have to say something a little bit different. She's right that there's something that's constant, but what's constant is its distance. So notice here, for this line, that distance is not changing. That means that the object is not moving at all. So it's not technically uniform motion if the object is not moving. Since distance is not changing, this object is stopped. It is not moving. It is sitting still at a particular spot over time, not going anywhere. Now, when you see a line that is horizontal like this, I would like for you to know that the slope is 0. If the line is flat, totally horizontal, the slope is 0. Now, would anybody like to ask any questions here? Josh, you had your hand up earlier. Did you have a question about this? No? So something like this, where all I'm showing you is the direction that the lines are moving, is definitely something I would ask you so that you can recognize if the slope is steeper, the object is moving faster. And if the slope is totally flat, so the slope is 0, the object is not moving. Now the third slide, which is on the back of the page, so you'll have to flip over, has one more example of a distance-time graph. So I can show you a couple of other points and let you try calculating slope. It will be very typical for me to ask you to calculate the slope of a line. When you calculate the slope, I told you you could pick any 2 points that are on the line, but I'm going to make some suggestions. When you're determining slope, if the point 0, 0 is available, choose it. It makes your calculation way easier. So in this graph, I can see 0 kilometers and 0 hours, that was a choice. It was right on the line in my graph. So if the point 0, 0 is on the line, I suggest that you pick it. You don't have to. You're not wrong if you don't pick it. I just think it makes your life easier. I also think that if the end point is part of the line, so most of the time your points will connect themselves. And I like, when I'm figuring out the slope, if it's possible, to pick the end point. Now, when you make a graph, one of the things that you'll notice is that not all of your points will line up perfectly. So this graph might have actually looked something like this. And so one of the things that you'll have to do when you're making a distance-time graph is to find what we call the line of best fit. The line of best fit is a math concept as well, but the idea is that you draw a straight line that connects as many of your dots as possible, but you don't play connect the dots. You don't go up and down and up and down and up and down making a zigzag. You try to follow the path of the most points possible. When you're making the line of best fit, you should try to make the points above the line and the points below the line be approximately equal in number. So if you look at this imaginary graph, I'm imagining that 2 points actually touch the line, 3 are above it, and 2 are below it. This is so that I can show you you're trying to make things as even as possible, recognizing that you might not be able to get exactly the same number. Your goal is always to follow the direction that most of the points are going in. It's like you're trying to take the average of the points and figure out where the line would be if you took the average of all of the points. Now, when you're picking your slope, you always need 2 points on the line. And so I would not, if I was figuring out the slope of this line, I would not choose this point or that one or that one or that one or that one. I would only pick a point that was actually on the line. And so that's why I recommend picking 0, 0 and the end point if they're there, because it'll make your calculation just a little bit easier. So if we were going to figure out slope, we know that we're always doing the change in y over the change in x, the rise over the run. In this graph, that's final minus initial distance over final minus initial time. So I need to remember that's my final point, that is my initial point. So the one that's on the left is always initial, the one that's on the right is always the final point. So on this particular graph, I'll take a read, and I'll see that for my final point, the distance was 300 kilometers, and the time for my final point was 5 hours. My initial point is a lot easier, 0 kilometers and 0 hours. So when you are subtracting 0 from something, you are not actually changing the value. So remember, kind of like I'm doing nothing over here. I am essentially doing 300 divided by 5. That means that my answer is 60. Since I was doing kilometers divided by hours, my unit is kilometers per hour. Now, based on the numbers on the graph, I should have one significant digit in my answer. So I will change this to 6 times 10 to the power of 1 kilometers per hour. Means the same thing as 60, but now I only have one significant digit. Now, does anyone have any questions that they'd like to ask about how you read a distance time graph or anything about how you calculate slope? So then we have one other type of graph and it is a speed time graph. On a speed time graph, speed will be on the y-axis and time will be on the x-axis. Remember that time is always on the x-axis. Now you might notice as you're looking at this that the word velocity is there instead of speed. I mentioned this word the other day to explain to you perhaps why a v is what we use for speed in a formula. Velocity and speed are measured with the same units, distance over time, and we'll see that the difference is one of them has a direction and one of them doesn't. But we can learn the same type of thing from those types of graphs, regardless of whether it's speed or velocity. So we would be measuring this in meters per second. Time down here would be in seconds. Now on a speed time graph, for now, until we talk about other situations, we should end up seeing a flat line. Now, since I just told you that the slope of a flat line on the other type of graph was 0, you can infer that that's the same thing that's true here. If I tried to calculate the slope, the change in y over the change in x, which on this graph is the change in velocity or speed over the change in time, I would do final minus initial speed over final minus initial time. Now, no matter which 2 points on the graph I chose, let's pick this point and this point. My speed is the same. I'm going 20 meters per second the entire time. So my final and my initial velocity or speed is the same value, 20 minus 20. For time, since I chose these 2 points, my time would be 3 seconds minus 2 seconds. That means that I would be doing 0 divided by 1. 0 divided by anything is simply 0. So my answer for the slope is 0. My unit, since I had meters per second, and then I divided it by seconds again, my unit is meters per second squared. This is the unit for acceleration. Now, since my object was not changing its speed, there was no acceleration. But when we get to the third section and we talk about acceleration, this graph will start having a slope. So for now, when you calculate the slope of a speed time graph, it should be 0. That means that there is no acceleration. That means that you have uniform motion. So notice the difference. On a distance time graph, a flat line meant the object wasn't moving. On a speed time graph, a flat line means the object is not changing its speed, not that it's not moving. And so there's a distinct difference there that you need to be aware of. Would anybody like to ask any questions about that part? So if the slope is just going to be 0 anyway, what could I figure out from a graph? Well, I could figure out the distance traveled. And the way I would do that would be to find the area underneath the line. Now what that means is that you'll take the line and make an imaginary little rectangle out of it. And we're going to figure out what the area of this rectangle is. Now we know from calculating surface area, let's say, that if I want to find the area of something, I need to take its length and its width and measure them together. So we'll say that because width is going across, that width is time. And that length, we'll call that the up and down, you could call it height as well if you wanted to, will be the velocity. That's what I'm reading off of this graph. So if I multiply velocity and time, that's the formula for calculating distance. So the area will represent the distance, the change in distance. So on this graph, I would multiply this, the width, 4 seconds, with this value here, we'll call it the length or the height, which is 20 meters per second. That means that my area under the line, so the distance that I have traveled, is 80 meters. Now, once again, I would want to have only one significant digit, so I would change that to 8 times 10 to the power of 1 meters. But that is what I could actually calculate on a speed-time graph. The slope for now should always be 0 because we have uniform motion. So the thing we'll actually be calculating would be the distance traveled by making a little rectangle under the line and finding the area of the rectangle. Now, does anyone have anything that they would like to ask about this slide here, about speed-time graphs? So there are some